So here we have a nice problem from the South Carolina high school math contest from the year 2016. And we have a nice geometry problem today that asks us to find the proportion of this regular hexagon that this red diamond covers. And there's also a note that comes with the problem that says that P and Q that touch this diamond are also midpoints of the sides of this regular hexagon, and also that the hexagon is regular, but I've already covered that. So let's go ahead and jump into the problem. First, what we want to do is split this hexagon into 6 equilateral triangles that cover the entirety of the hexagon. And we know this is possible because all of the side lengths and angles on this hexagon are equal by this regularity statement right here. So now we have a picture that looks like this. But now notice, if we find the height of one of these triangles that goes from this dot to either P or Q, that's going to be perpendicular to the side of the hexagon, but it's also going to be perpendicular to this big bisection of the hexagon that we have right here, this long bisection right there. And so we'll get 2 big red triangles. We'll call this point A and this point B. So we'll have triangle APB, that area, plus triangle AQB, and together they make up the entire area of this red diamond. So if we can find both the height of this yellow triangle here and the length of this bisecting line segment AB, then we'll be set to go on calculating the area of this red diamond. And we can use the area of the triangle and multiply it by 6 to get the area of this regular hexagon. So let's go ahead and do that. The area of this triangle, this small equilateral triangle that we've split this hexagon into, that's going to be equal to 1/2 base times the height. And now it's up to us. We can choose whatever variable we want to be the base here. And that variable is going to equal all of the side lengths of this hexagon, as well as all of the yellow line segments that we have drawn here, because we've established that all of these triangles are equilateral. I'll use A as the side length here because it just seems like the natural thing. So we'll say 1/2 A. That's from this line segment here. But now we have to calculate the height. And the height here is going to be calculated using the Pythagorean theorem. So we know that the height squared plus 1/2 A squared is equal to A squared. So let's go ahead and write that down. We have A over 2 squared plus the height squared equals A squared. Again, that's because this segment that I am coloring in blue here is equal to A over 2. And the yellow segment right here is equal to A. And using the Pythagorean theorem, we can find this yellow segment that I'll recolor in orange just for a little bit of clarity. That is H in this case. And like I said, they're all related using this Pythagorean theorem here. So let's go ahead and calculate out H here. So we have H squared plus A squared over 4, that's by squaring this object here, equals A squared. And now we can subtract this A squared over 4 from both sides to get H squared equals 3/4 A squared. But now we can take the square root and only the positive square root because we are working with lengths here. And that makes the most sense. So now we have H equals the square root of 3 over 2A. But now let's take this height here and plug it back into our area formula for this equilateral triangle. So that will give us 1/2 A times the square root of 3 over 2A. That's by this red box down here. But now we have the square root of 3 over 4A squared. And that's equal to the area of this triangle. And in the process, we've also found the height, this orange H here, which will also let us solve for the area of the diamond at the end of the problem. But first, let's go ahead and multiply this equilateral triangle by 6 because we have 6 copies of this triangle throughout this hexagon. We have 1, 2, 3, 4, 5, and 6 copies. So let's multiply that by 6. we get 3 times the square root of 3 over 2a squared. And this is equal to the hexagon that we have on the board. Okay, so let's clean all of this up and then calculate the area of the diamond and compare it to the area that we've calculated for the hexagon. Okay, we're just about ready to finish this problem off. We've calculated the area of the hexagon up here, and we also brought up the height of this triangle here, which also happens to be the height of this big red triangle APB and AQB. So let's go ahead and calculate this area now. So we'll have 1/2 base times height, but the base in this case is this long diagonal AB that we established before. But now that we've given a length to this equilateral triangle, we talked about this in the last board, that's what we called A. So this is going to be 1/2 times 2A. That's because it goes across 2 copies of this equilateral triangle. To this point is 1A, and then all the way across to the other side of the hexagon is 2A. And then we have our height, which is the height that we calculated before. That's the square root of 3 over 2A. And so now, after some quick multiplication, we have the square root of 3 over 2A squared is equal to one of these red triangles. But notice I said one of these red triangles because we have 2 of them. We have triangle APB and triangle AQB that I've put up here. So the entirety of the area of this diamond is equal to 2 times this thing, which is going to be the square root of 3A squared. So let's go ahead and divide the area of the diamond by the area of the hexagon to see how much of the hexagon it actually covers. So we'll have the square root of 3A squared, that's from the area of the diamond, divided by 3 times the square root of 3A squared over 2. That's from the area of the hexagon. But now let's go ahead and multiply and simplify the bottom half of this fraction. So we will have 2 over 3 times the square root of 3A squared on the bottom. And we'll also have 2 over 3 times the square root of 3A squared on top. And this whole bottom thing here is going to cancel. And so we just are left with this top bit here. But notice our square root of 3 in the top here and the bottom here cancel. And the A squareds also cancel. And that just leaves us with 2/3. So that tells us that this diamond covers 2/3 of the hexagon that we have up here. And that's enough for now.